Imagine you're standing at the edge of a field trying to predict how much wheat will grow based on how much water you'll provide. That's essentially what linear regression does. It connects cause and effect. It's the simplest, yet one of the most powerful tools in a data analyst's arsenal. At its core, linear regression is about finding relationships, quantifying how one thing influences another. But here's the catch. The relationship has to be linear. That means for every increase in X, like adding more water, you get a predictable and proportional increase or decrease in Y, like more wheat. For this magical process to work, a few ground rules need to be in place. Linearity. The relationship between variables should follow a straight path. If you're trying to model the flight of a paper plane with a straight line, but the actual path loops and dives, you're already off course. Independence. Each data point should stand on its own. Imagine trying to predict tomorrow's weather based on today, and the past week's observations have secretly ganged up to influence each other. Linear regression doesn't play well in those scenarios. Homoscedasticity. Fancy word, simple meaning. Your prediction errors should be consistent across all values. If you're trying to predict house prices, your error can't balloon for mansions and shrink for tiny homes. Normality of residuals. Those little prediction errors we just talked about, they should be random and normally distributed, like a fair roll of a dice. Now, let's get to the math. The equation that runs this show is y for v0 plus v1x plus a. Think of v0 as the starting point, your intercept, while v1 is the slope, the rate of change. And A? That's the unpredictable randomness of life, the error term. Together they form the line that minimizes the gap between predicted and actual values. Linear regression is built on data. Step 1. Gather your numbers, both dependent, what you're predicting, and independent, what's driving the change. Then, let algorithms like ordinary least squares, OLS, do the heavy lifting, crunching numbers to calculate the slope and intercept. Finally, evaluate how well your model performs using metrics like R-squared, which tells you how much of the variation in Y is explained by X. Linear regression is everywhere. Businesses use it to forecast sales based on marketing spend. Economists use it to study relationships like unemployment and inflation. Farmers use it to estimate crop yields based on weather conditions. The possibilities are endless, and the simplicity of the method makes it a favorite across industries. But let me tell you, linear regression isn't without its challenges. Misuse it, like trying to fit a straight line to data that's clearly curving, and you're setting yourself up for failure. This is why understanding the assumptions and limitations of the model is just as important as applying it. As we dig deeper into regression techniques, linear regression will always remain our foundational block, a tool we'll keep coming back to time and again.